Alright, so let's talk about this calorimetry stuff that's required to actually required knowledge for the question number 6 and question number 7. So let's just talk about this one. This is what a calorimeter looks like, by the way. We don't have laboratories for this semester, so you may not see this one, but in the chemistry laboratories there is a good looking equipment which probably costs like $100,000 or so to actually measure the heat of the material, and heat coming out of the specific mass of the material. So inside there is a water that's inside of this. This is a pure water, right? And you put the reactant here, and that reactant is going to be reacting with oxygen, and then it's going to produce a fire inside, right? And then it's going to burn off, and then gives out the CO2, and then probably water a little bit, right? And by combusting everything inside, that heat is going to be transferred from this system inside of that container to the outside of the container, which is this water right here, right? I meant the container is this one. That's your system, right? So the heat is actually transferred from the system to the surrounding, right? To the surrounding, which is the water right here. And by transferring the heat from inside to the outside, the water temperature is going to rise here. And you already know the exact volume of the water that's in the surrounding. And then by measuring the change in the temperature of the water right here, you can estimate the heat that's released by the system reacting with oxygen. And that's really the calorimetry equipment that's how it works. So calorimetry is the study of measuring the heat exchange of the chemical reactions. So that's what's happening here. And then because this one right here is it's really you can actually think of it as delta H, the enthalpy of the reactions. It's actually slightly different, but the error in that is very small. So this one right here is probably much closer to the delta H, because this one right here, the pressure inside of this styrofoam cup is more than likely it's 1 atm before and after the reaction, because you can't really seal, you can't make really the perfect closed container with styrofoam cup, right? So that one right there is going to be the constant pressure, so it's going to be closer to delta H. But either way, that error is going to be significantly small, really small values. So what you're measuring is the temperature change of the surrounding, which is the temperature change of this water right here. So the heat lost by system is going to heat up the surrounding, right? And the temperature of the surrounding right here, that the change in the temperature of the surrounding times the mass of the water times the specific heat, which is the energy required to increase the temperature of the water by 1 degree Celsius for 1 gram of water. That's what it is. So that's called the specific heat. And that Q surrounding is given by that one, right? Because Q system is the negative, then Q surrounding is a positive value of the Q system, which is this one, right? And surrounding water is used. So these are the formula that you are going to use to solve some of the problems. Okay, So just by using your common sense, which one of these processes require more energies? Increase the temperature of 100 gram of water by 10 degrees Celsius, or increase the temperature of 200 gram of water by 10 degrees Celsius. More mass is going to require more energy, right? So yeah, this one requires more energies. What about this one? Same mass but different temperatures. Which one require more energies? It's that one, right? Because to go from 0 to 10 and then 10 to 20, right? This one requires a little bit more energies out of that, right? So, and that also another stuff, which is 100 gram of copper by 10 degrees Celsius or the 100 gram of water by 10 degrees Celsius. That one could be difficult to answer if you don't do the cooking. But if you do the cooking, there is a reason why that we use a copper pan. The copper is very easy to heat it up compared to water. Water is hard to heat it up. So the copper, heating up the copper is much easier than heating up the water. So if you combine all of these guys, right, then you are going to get that formula right here. Mass of the water matters, mass of the material matters, the temperature change matters, and then also the substance, the property of the substance matters for heating up, right? So all of those specific heat is given by this table. You don't really have to remember any of these guys, but you might want to remember this one right here. Specific heat of water is 1 calories, which is that one, 4.184 joule per gram of water per degree Celsius. And everything else is that. So what did I say about copper? It required 0.385 joule of energy required to heat up the 1 gram of copper by 1 degree Celsius compared to the water is 4.184 joule, right? So you need a lot more energies to heat up the water than copper, right? As I said, the copper is used for cooking equipment just because of that reason. Alright, so specific heat is that by definition it's the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. Unit is a joule per gram per degree Celsius. And delta T is always the final temperature minus the initial temperature, right? Final minus initial. That's always this triangular things look like. And that formula is given by this formula right here. Now you're wondering that why I don't have the negative sign right here is what depends on what you're looking at. If you are looking at this picture right here, right? If you're looking right here, if you're interested in the water right here, that will be your system, right? But if you are looking at the inside of this container right here, that's the system, that's the surrounding, right? So that's the difference between the positive and negative. It really depends on what you're looking for. So going back to all the way to here, this one right here is whatever the things that you are looking at is made out of the particular substance, for example, like the potato chips, right? And that's inside of that container. And then multiply by the mass of the potato chips, and then multiply by the changing temperature of the potato chips, or whatever the things it became for the product. That's going to be the heat that's related to that specific stuff that you're looking at. So heat capacity is the amount of heat required to raise the temperature of an object by 1 degree Celsius. So what's the relation between the specific heat and the heat capacity? Heat capacity is this capital C right here, and the specific heat is ms delta T, right? Just forget about these things right here, just making it as a positive right here. Then ms is actually equal to this C right here, right? So the mass times the specific heat is the heat capacities. Alright, so calculate the amount of energy required to heat up the 95 gram of water from 22.5 to 95.5. So how do I actually do these things? You're going to use this formula right here, and then temperature change is 95.5 minus 22.5, right? And then this is water, right? So water specific heat is 4.184, and then mass is 95. So if you actually put all of these things in there, you get that value right here. Okay. Now you can do these things at home by yourself, so check that. And all of these things, just try to solve all of these problems at home, and then ask me questions if you have anything associated with that one. Then I should probably stop here, but let me just keep on going a little bit more. The standard enthalpy of formations, this one right here, is under specific conditions. 1 atm at 25 degrees Celsius. What is the energy required to put together all those atoms into the molecule? That is really the standard for enthalpy of formations. And these things are usually tabulated in the table. So if you use the table, you can actually calculate. The enthalpy of the reaction, because you can always get the enthalpy of formations from each molecule, and then depends on how many molecules of those things that you used to create certain amount of more of the product you produced. Each of those numbers have the standard enthalpy of formations, and then you can actually calculate the enthalpy of the formations. Please read the textbook, and then it's not that difficult. So that will end the last part of the thermodynamics.